So we've now described the model more or less. There are tiny assumptions that we change bit by bit so that the model becomes more and more complicated and more realistic over time. First, easiest assumption is that the signal, interim signal, can be observed and verified without any cost. So the difficult question of how does the information get into the financial market, who is the one who's going to search for the cost, who speculates based on the cost, that's left for later. So now the contract can depend both on the signal and or on the final outcome. Um, and possibly it could depend on both, but because of our assumption of the sufficient statistic, that the signal is a sufficient statistic, the contract will depend only on the signal and not on the final outcome. We're going to check later what the difference between a contract that depends on the final outcome and one that depends on the signal. And we will see that the one that depends on the signal is better. Okay, so let's see what happens if the entrepreneur receives some RB after the good signal and zero after the bad signal. So that means now that he's compensated early, already at the date of the signal. He doesn't have to wait until the final outcome. So then the incentive compatibility requires, now if he works hard, the probability of a high signal is sigma HH. Okay, so he will get the RB with probability sigma HH. If he shirks the probability, sorry, this should be a sigma, the probability that he still gets a high signal, it's still possible. So that's then sigma LH, and then he still gets the RB, plus he collects the private benefit B. So the first one has to be larger than the second one. So we can rewrite that as sigma HH minus sigma LH times RB has to be larger or equal than B. So therefore, now the non-pledgeable part of the final outcome of the NPV is now then the entrepreneur in equilibrium, he will behave or she will behave. So she gets something with probability sigma HH. What does she get is RB. And that's then identical to sigma HH over sigma HH minus sigma LH times B. Okay? And if you compare that before, I'm going to write that in a different color. Before, what we had was pH over pH minus PL times B. So that was the expression that we had in the model 3.2. So that would also be the expression that we would get for the non-compressible share that we would get if we would make the contract depend on the final outcome and not on the interim signal. Okay, so the question is, of course, in which case is the incompressible share bigger? And one thing that's important to note, let me go back to this slide, is that for the entrepreneur, having a big incompressible share is something that's bad. I mean, the incompressible share is the minimum that the entrepreneur must get. And one would probably typically think, well, if I get more, that's good. But here, the thing is that if the incompressible share is bigger, it just increases the likelihood that the investors will say that they will not finance the project. Okay? Um, there are just two different cases that can occur. One is that the incompressible share is large, such that there is no finance at all. And if there is finance, the entrepreneur will get the complete NPV anyway, independent of the incompressible share. Okay, so therefore, it's a little bit confusing that having a big incompressible share, a big non-pledgeable income, big part of that pie, that's something that's bad and not good for the entrepreneur. Okay, so we have this new condition for obtaining finance. That's now PHR minus the sigma fraction times B has to be larger or equal than I minus A. And this fraction here before, so this fraction before, that was PH over PH minus PL. So that's equal to PH over delta P. There we could write delta P. Here, writing delta sigma, that would be possible, but it's a little bit more difficult because we have four different sigmas, so it's not so clear which difference we're talking about. All right. And now, interestingly, uh, there is a direct comparison that this pH fraction is larger than the sigma fraction. So that means that the incompressible share has gone down, and that means that with the early signal, it's easier to attract finance. So the early signal, putting the early signal into the contract is helpful. Okay. Why does this hold? Well, we can substitute the pH. We know that the pH has this definition from two slides before, sigma HHVH plus sigma HLVL. We can write that slightly differently over such a difference here. Same applies to the pH minus PL. So in both cases, we get, if we substitute the definition of the VLs, we can reformulate a little bit. And then we see here that this VL term that's added here, if we set that to 0, then the VH minus VL, the delta V, that cancels out, factors out. So therefore, adding the VL increases the fraction, so therefore this fraction is bigger in the final one. Okay, this is an important insight. It means that if early information is available, we should use it. Why? Because over time, additional noise could be added, and that's noise that influences the outcome of the project, but is not related to the moral hazard problem. But we want to attack the moral hazard problem. We do not want to, if we could, we wouldn't want to reward the entrepreneur for success, but for putting in effort. The effort is what matters and not the success. Okay, so therefore, if we have a signal that's closer to the effort, we're going to take it even if it's unrelated to the success. Okay, so so this means that crazy things might happen, and you can think about yourself how we can whether that makes sense. For example, it could be the case that the entrepreneur is diligent, he's working hard. In effect, in equilibrium, he's always going to work hard. Or she's always going to work hard because of incentive compatibility. So we know that she's always going to work hard. But let's assume now that the signal is still negative, or she gets a negative signal. Okay, then she doesn't get a reward. And let's assume that the final outcome is then again positive. So we get the R. Then it's kind of a strange situation. She's worked hard. The entrepreneur has worked hard. And we know that she's worked hard because of incentive compatibility. But still, we've said, okay, bad luck, you're not going to get anything. And then we have waited until the final time. The firm was even successful. And now she could come to us and say, look here, that's the proof. Firm has been successful. I've worked hard. You know it. Now give me some remuneration, give me some compensation. And the investor would say, no, that's not part of the deal. If that were part of the deal, if we would remunerate in the case of success, if she's worked, then we would be back in the old case, and then we would get this, or maybe even something worse. Okay, so therefore, yeah, it's only early compensation based on the interim information. Okay, let's now, this was slide number or step number 2, so the optimal contract. But let's now look at the implementation. How can this kind of contract be implemented? Okay, so we now assume that this early signal is observable. It does not have to be verifiable by court. Well, that's an interesting distinction. It means that everybody sees the information, but it's not something that can be used in court. So it could be some kind of soft information. Everybody knows it, it cannot be part of a proof. So that means the signal itself also cannot be part of the contract. We cannot say if the signal is high, then there is a reward. Okay, but there's a way out. And that's the cool thing, it's the stock market. The stock market is turning soft information. Any information moves stock prices, no matter whether it's verifiable or not. Okay, so um, it so we have soft information, non-verifiable information. Still, the stock price of the firm moves, and then if we make the contract contingent on the stock price, then we have solved the verifiability problem. So therefore, the stock market can be seen as a mechanism to turn any information, especially also soft information, into verifiable information. Okay, so it could let's see the publicly traded shares. Number of shares is normalized to 1, so there are 100% of shares altogether. And so that means that the interim value in case of a high signal is VH times R, because we have assumed that if the signal is high, then probabilities are such that the success probability is VH. That's the definition of the V. Now, otherwise, it's VL times R, depending on the information. So we now have the following contract that says, okay, here, entrepreneur, if the stock price goes up, then you're going to get a fraction X of the shares. If stock price goes down, you get nothing. Okay, so it's actually, this is what's written here, it's like a stock option that is originally at the money. If the price goes up, it means that the entrepreneur gets something. He can cash in his stock options. If the value goes down, it's out of the money and he loses. He gets nothing or she gets nothing. Okay, what's the value of the X? We have, I'm going to use blue again, otherwise it looks like everything is wrong. So the X is given by X times VH times R is equal to RB star. Okay, now that means if the value goes up, I'm going to get X shares, and the value of each share is going to be VHR. So X times VH times R is the aggregate value of this share package. And RB star, that's meant to be my compensation from the slides before, the compensation in case of a high signal. Okay. So this is the equation that defines my x depending on RB star. And what determines RB star is just break-even constraint of the investors, PH times R, minus with probability sigma HH. I have to pay this RB star. And this has to be equal to my initial investment, I minus A. Okay. So this defines RB star. And then from the equation above, the RB star, that defines me my X. Okay, so this is a stock option plan, really what we get. So I think this is a cool interpretation that we have introduced in management that is compensated by such a stock option plan in equilibrium. So we have proven why, we've shown why such a stock option plan is something good. In reality, there is a political discussion about stock option plans, and often it's argued that stock option plans for management, stock options as compensation for managers, that they set bad incentives, that they make them take too risky decisions, make them risk loving, and they also induce them to short-termism, that they take only short-term decisions. Okay, and one can ask oneself what kind of those arguments is reflected in our model here. And the answer is, well, this model is not about risk taking. It's an effort decision that the entrepreneur takes and not a risk decision. So our this model cannot say anything about that. And what about short-termism? Here, short-termism is something good. It's optimal if the entrepreneur tries to move the price in the short run, because in the long run, there's lots of stuff that can happen. Okay, so it's good for the entrepreneur to be interested in the short run, and that automatically leads to an optimal behavior also for the long run. So, yeah, interesting discussion, I think.